Okay, so this video is going to help you hopefully with your lab on the 3-channel equalizer. Um, I am not going to take credit for all of these notes here. These are notes that were really created by Professor Byers, but I'm going to go through and explain these on doing filter design. Now, there are several types of filters out there, um, and depending on the application, determines on what type of filter you would like to use. The filters we're going to use are Butterworth filters, and if you research some of the reasons why you want to build filters, these are generally good for audio. And the reason is because they typically have a low, not a low, a flat pass band, so that we're not getting any kind of weird distortions in the pass band where you might get small bits of amplification going on. All right, so now the assignment was saying that you need to have at least a fourth order. Amplifier, and we're going to go ahead and go through that here, but before we get into that, there is some quick things here that I'm going to not go through all the details, but it has to do with magnitude and frequency scaling. Because typically what's going to happen is we're going to have a filter that's designed for basically 1 radian per second 3 dB cutoff, and then we're going to magnitude and frequency scale all of the components so that we wind up with the correct cutoff frequencies. Okay, so magnitude scaling here by a factor of km. So we're basically increasing the size of components. And the way that works here is if we have the new value of a resistor would be K sub m times the old value of the resistor, and the new value of an inductor would be equal to K sub m, the old value of the inductor, and then finally the new value of the capacitor would actually be the old value of the capacitor over that, divided by the K sub m. And that just really has to do with the impedance equations. Impedance for resistors R, impedance for inductors J omega L, and impedance for capacitors 1 over J omega C. That's why we multiply by Km for the inductors and why we divide by Km for the capacitors when we're doing magnitude scaling. And so what we're saying here is an example of a magnitude scaling. An example is, let's start with R equals 1 ohm, L equals 10 henries, or not 10 henries, that's going to be a stupid one, 1 nanohenry, and C equals 1 farad. And we are saying that, well, I want to use a resistor of 10 kilo ohms. So if I want to use a resistor of 10 kilo ohms, basically we can determine by Km by just saying, well, my new value of the resistance is 10K times Km times 1 ohm, so Km is just 10,000. And then from that, we get then that the new value of the inductor, by doing the scaling, would be 1 nanohenry times 10,000 which gets us 10 microhenries. And the new value of the capacitor would be 1 farad divided by 10,000, which would be 100 microfarads. And so we're able to scale things based off of that. So that's magnitude scaling. Frequency scaling is if we're wanting to change the frequency that a circuit is operating at. And so frequency scaling, without going through all the details, we want to have KF being my frequency scaling. And now resistors aren't affected by frequency, so the resistor values won't change. The inductor value, again, skipping all the details of why, this just comes from the impedance equations, 1 over KF L old, and you actually do the same thing for the capacitors. So what you can do is you can summarize this for scaling here is that R new is equal to Km times R old. L new is equal to Km over Kf times L old. And C new is equal to 1 over Km times Kf times C old. Now, it turns out that the most common ones we'll be using here are the resistor and capacitor, because we're not going to typically use the inductor one. So we're going to need to use frequency scaling here with that. Now, the next thing is to look at Butterworth filters here. And, oops, that's not what I wanted to bring up. This is what I wanted to bring up here. So this is, again, and you can look this up here. This is normalized denominators. In other words, the transfer functions for filters based off of the order that you want them to be. And this is going to get you that nice flat behavior and then the 3 dB point where you're wanting it to. So the mistake I told some people is just to do 2 second orders cascaded together. That is correct. You are going to 2 second or biquads cascaded together. The issue is, if you look at the transporter for a second order, it's 1 plus 1.414 s plus s squared. But for a fourth order, that 1.414 is not there anymore. We have 2 different values here, 0.765 and 1.848 here. And so that's going to be important for us here. So the denominator, the normalized denominators give us the Q factors, the quality factors that we need for these Butterworth filters. And we're going to have 2 of them here. Okay, so if we're looking here, just lost my place in my notes here, sorry. If we're looking here, we should really know kind of how these things are doing here. So these Butterworth filters, as I said, give us these Q factors, and basically, let me go back to the PowerPoint. The numbers in front of S are the Q factors that we are going to want to use. So for the biquad stages here. So if we see here we have 0.765 and 1.848 for a fourth order filter. So for a fourth order filter cascaded using 2 second orders, we want one of the Qs to be 0.765, and we want the other Q to be 1.848. Okay, so those are what we're going to want to have here for our Q values for our fourth order filter. And that's just from this table. And this, you might say, where is this table? This is one of those things that's just published. I mean, this is well known. People use this all the time. Okay, there is theory behind why these poles are in these particular locations, but that's going to be beyond the scope of this course, and that would be for like the course that deals with circuit synthesis. Okay, so fourth order cascading using 2 second orders. All right, so let's now talk about what's called the Sallen-Key topology. So the Sallen-Key topology is just one way to build second order Butterworth filters. So the way we're going to do this here is we have the following is a low pass filter. And by implementing it this way here, I'm going to put in component values here in a second. The key thing is this has unity gain. Because right now for this first lab here, we're just trying to get these to have unity gain here. And we can worry about the gain in later stages. And that's typically what you want to do is you don't typically filter and gain at the same time. You do your filtering and then you might do your gain. Now these component values, there's different ways to have these be, quote, normalized. But one typical way of doing this is 1 ohm, this is 1 ohm, this capacitor value is 2 times whatever the quality factor is, and this is 1 over 2Q, whatever the quality factor is. And that's again to spread the poles out here. So, and this is of course having what's called K equaling 1 here. And so this is what we're going to be doing here. And this actually gives us a 3 dB equaling 1 radian per second as far as what this would be. Now I know there's no capacitor values in here yet because we don't have the Q factor, because the Q factor depends on how many stages we're putting in and what the overall amplifier is going to be. Okay, so the overall, not amplifier, filter. The overall filter is going to look like this here. me make sure to draw this in the correct location, like that. So this is going to be my fourth order low pass filter. And we're going to have R1, R2, C1, C2, R3, R4, C3, and C4. And then the first stage quality factor, Q1, is equal to 0.765. And this one, the quality factor, is equal to 1.848. Now, the way Byers teaches us how to do filter design, it's slightly different than what we're doing here, because we're deciding what the cutoff frequency is, as opposed to there's this WP and WS, because there's this trade-off between order and how steep you can make this. We're just making fourth orders with a particular cutoff frequency. So I'm just going to arbitrarily choose my 3dB to be 1 kilohertz. But that means omega is 2 pi kilorads per second, because omega is just simply 2 pi f. Great. So we've got that now. So now, believe it or not, all that's remaining is magnitude and frequency scaling. So this might require trial and error. And the reason is well, you have to pick a value for R1. And what I'm going to do here, and this is something that we often will do here to make life easy, or sometimes what you do is you pick certain capacitors to all be the same value, but I'm going to just let all the resistors, in this case, be equaling 10 kiloohms. Now, it doesn't mean they have to be 10 kiloohms. You could have chose 15 kiloohms. You could have chose 12. You could have chose 1 kiloohm. And actually, the 10 kiloohm choice that we made here might be wrong. I might have to go back and redesign, because I have to then make sure that I get capacitor values that make sense. And the reason I'm saying this is this capacitor value here, remember, these are 2Q1. This would be 1 over 2Q1. And this is equal to 2Q2. And then this is 1 over 2Q2. Now, let's remember all of my frequency and magnitude scalings here. So what we have here is, okay, well, I started out with this original topology having 1 ohm here. So I've made them 10 kiloohms. So my magnitude scaling is 10,000. Now, this was for 1 rad per second. I am now at 2 pi k rads per second. So my frequency scaling is 2 pi kilorad per second. And now it just becomes a bunch of formula plug and chugging, because I've set R1, R2, R3, and R4 all equal to 10 kiloohms. And now to get C1, well, C1 would be 2Q, so it's 2 times 0.765, but then I have to scale it by the appropriate factors, and with capacitors, we divide by both the scaling factor, so it's divided by 10,000 times 2 pi kilorad per second. And so if I do that, let's see what we get. And I wind up getting 24.35 nanofarads for the first capacitor. Okay, well, now we just go through, and then that's a reasonable value for the capacitor. If I had gotten picofarads, that's a little small, though we could make picofarads work if we were building or etching a board. But if I had gotten something like millifarads, well, that doesn't make sense either. So we have to, again, pick values that make sense. But then let's go through here and figure out what C2 would be. Now C2 would be 1 over 2 times 0.765 times 10,000 times 2 pi kilorad per second. So I now have to go back and redo this. And I get 10.40 nanofarads when I do that one. And now C3 and C4 are done the same way, except now my Q factor is 1.848 divided by 10,000 times 2 pi kilorad per second. And let's go ahead and do that computation. And I get that this one is 58.82 nanofarads. And C4 would then be equal to 1 over 2 times 1.848 times 10,000 times 2 pi k. So if I do that computation, I wind up with 4.31 nanofarads. And so I now have my design complete, and I could go ahead and simulate this. So there are other ways to do this, but the method that Professor Byers describes in his notes, which is what I borrowed from, is actually the best way to get your 3dBs to be in the correct location with having a nice flat pass band. And so now, as I said, you could put in 4th order filters or 5th order filters if you wanted to. I'm sorry, 5th or 6th order filters if you wanted to. You'd have to use different values on your Q factors here. So like, you know, if you used a 6th order filter, notice the 3 different Q factors that you would have, and you'd have 3 stages. I would recommend just doing a simple 2-stage unless you've already done something else. And so this is a way to get the 4th order low pass. Now, one thing I want to mention here, to get a 4th order band pass is actually a little interesting. It's actually a 2nd order low pass cascaded with a 2nd order high pass, because that's still considered 4th order because you have 4 poles in it. So if you're thinking about the 4th order band pass, we would be using the normalized denominator of 1.414 for the Q factor for that. Okay? So hopefully this helps. I'm going to throw together a video with the simulation as well.